earlier in the afternoon. So this is actually work in progress. So the paper is not on the archive yet, but hopefully it will appear semi soon. So this is joined with Ban Junmeng, who's at Johns Hopkins. So this is work in progress. Okay, so let me first tell you the more classical story, which is basically the work of Hassett. So Hassett studied the moduli space of stable curves with weighted points. So this is the moduli space of stable curves. Of genus G with a bunch of points, but weighted. And the weights are given by the coefficients in this vector A. Okay, so let me say this like A1 through AN. They are all positive. And okay, so they are between 0 and 1. So basically the object parameterized by this moduli space is a curve of stable curves of genus G together with these mark points. Where these are in a smooth locus of C. Okay, right, so that's the object. So it's a compact and even projective moduli space. So what Hassett studied, and one of the things that Hassett studied is that so he showed the following. So of course this moduli space will depend on the coefficient A that you choose. So what he showed is that if you vary these weights, so if you choose two different weights A and B, then you can compare these two moduli spaces. And in fact, there is a natural birational morphism between these moduli spaces when you drop the weights. There exists natural reduction morphism. From weight A to weight B, where at the level of objects, what you are doing is by taking one stable curve with those weights, and then you replace the coefficient from A to B. Then, so maybe I forgot to say, with weighted points such that the canonical plus this boundary is ample. So this is the stable condition. Right, so then once you replaced the weights, then this might no longer be ample. Okay? And so what you have to do is to contract the components where the degree becomes negative or 0. And then contract the components of C where the degree of this, can people see it here? Where the degree of this log canonical divisor becomes non-positive, right? So for instance, if your C is like this and you have these two mark points, so initially the weights are A1 and A2, and then if you go here, so let's say this is like a P1 here. Maybe I should draw it on the other board. So if you have a P1 component here, and then you start dropping the weight, and then the sum of the weight becomes less than 1, or maybe less than or equal to 1, then the degree of canonical plus the boundary is not positive on this component, so you have to contract it. So the replacement would become this curve with two mark points colliding. Okay, so then we're just P1, so where P1 equals P2 becomes the point where the curve becomes contracted to. Sorry? So it won't become all negative because the total degree is going to be so of course this weight has to be in the admissible range. Okay, so and is admissible, meaning that so even for that moduli space, in order to have a non-empty moduli space, what you have to require that the degree of this has to be positive. So in particular, admissible means that this condition is satisfied for B. Okay, so as soon as the moduli space is non-empty, you can always do this. Okay, so that's the reduction part. And of course, this only works if the weights are strictly larger than or equal to the other. So what happens if you choose two weights that does not have this monotonicity? So then there is also a Wall-and-Chamber decomposition for the admissible domain. So there exists a finite and rational polyhedral decomposition of the set of admissible weights. So as I recall, this basically means that the moduli space there is non-empty. And what does decomposition do? So basically, it's a decomposition corresponding to the different models that you see over there. Okay, so such that this moduli space stay the same if you choose the weight in the same open chamber. It's the same. Let's say it's independent of B whenever. So let's say this decomposition is like this. So where the PIs are one of the polytope. So as long as you vary the coefficient vector inside the interior of an polytope, then this space doesn't change. And if you, so then maybe I can call this MI, since it's independent. And then if you have a face of the chamber, then there's a wall crossing morphism. So if let's say Pj is a face of Pi, then again there's a similar morphism that compares to different moduli spaces. Then there exists, let's say, a wall crossing morphism from Mi to Mj. So basically what this says is that as you vary your coefficient, there are finitely many moduli spaces that appear there, and there are only finitely many morphisms that you can use to compare these spaces. So, but of course, once you drop the weights, there is always this kind of comparison. So that's the yes. Yes. So if you take from the interior to the boundary. So basically, again, what you do is if you specialize this coefficient to a certain boundary, then the degree of that component may become 0, so you have to contract it. So that's the replacement. Yeah. So it's always from the interior to the boundary. So these two are basically the natural structures between this moduli space that one can expect. So what I would like to talk about today is some higher dimensional generalization of this picture to a moduli space of higher dimensional object. So what's this higher dimensional object? So by now it's pretty standard that so the higher dimensional replacement of a stable curve is called a stable variety. And this was introduced by Collar and Schaffer-Baron in the 80s. So the prototype of a stable variety is this. So so it takes a variety of normal crossing singularity. Just like a stable curve is a curve with normal crossing singularity. And you want a condition of ampleness. So let's say canonical bundle is ample. Of course, this is not enough if you want to compactify the moduli space, because so for instance, you can have a smooth surface degenerating into something with ADC singularity. But of course, AD singularity is not normal crossing anymore. So if you want to compactify moduli space, you'd better add this kind of stuff as well. So what turns out here is that, so these are basically canonical models of smooth surfaces. So what you can do here for replacement, so you want to replace this with not varieties with these two conditions, but rather log canonical models of normal crossing varieties. Okay, so we replace with ample models of normal crossing singularity, normal crossing varieties. So basically, this gives you this stable variety. And moreover, we would also like to talk about weighted points here. So in the higher dimensional case, that would give us a boundary divisor. So it's known that if you take these ample models, the singularities you end up with is what we call the semi-log canonical singularities. So they are no longer normal crossing. But in higher dimension, that's the best we can hope for. So so in general, if you want to talk about the higher dimensional theory, the correct object to parameterize in this moduli space would be the so-called stable pairs. So these are a pair consisting of a variety and the boundary divisor, where where this pair has semi-log canonical singularity. I'll just abbreviate it as SLC as always. Okay, so and moreover, we would like to require the ampleness condition. So kx plus d is ample. In particular, semi-log canonical would mean that so this d, so for instance, the coefficient of d is between 0 and 1. Okay, so I can just write d as a sum of ai plus di, and then if I fix my weights ai, I can talk about the moduli space. So one of the big theorems in the past several decades, which follows from the work of Collar, but also but there are also works of Hopkins, McKernan, Xu, etc., and maybe plus several others. So it follows from this theorem, what this theorem says is that, so if you consider these stable pairs, then there is also a projective moduli space parameterizing this kind of higher dimensional objects. Okay, so if I fix a dimension. Okay, so this is going to be my dimension. And if I fix the coefficient, okay, so this will be the coefficient of my boundary divisor. And I also need to fix some numerical invariant just as those 2g minus 2 plus the sum of the weights over there. So those are basically the degree of the log canonical divisor. So here we are fixing the volume of my log canonical divisor, so which is just the self-intersection number since they are ample. So once you do this, then there exists, and let me just say a proper moduli space. If you want projective, I need to put more names over here. Proper moduli space space parametrizing the stable pairs with this numerical invariant. Maybe I should say proper Berlin-Mang first. Maybe that's the better word. But of course, if you take the cost moduli space, they would parameterize the same set of objects. Okay, parameterizing stable pairs with the above invariant. Right, so let's say between 0 and 1. Right, so it have to be close under addition, let's say. Yeah. But let's say, so if you just look at the like the generic member, then that's okay. Right, so another way to do it is you can absorb some components in the DI, but that's fine. Okay, so all right, so are there more questions? Yeah. So there are different ways to do it. So either you absorb it into the ways you write the decomposition, or if you want to require the components are prime divisors, then you have to choose coefficient sets that are close under addition. But that's fine. Okay, so all right, so we have these moduli spaces. Now you can ask the same question. So if you drop the weights, are there similar reduction and walk crossing morphisms between this moduli space, and is there a finite one-chamber decomposition? Okay, so that's the question that we would like to address. So let's already write it down. So this reduction and walk crossing for this moduli space, and maybe I should give it a name. So so since I'm mostly interested in changing the coefficient, so I can just keep the dimension fixed. The volume will not stay there during this process. But I'm not going to worry too much about this. So let me just put all the components together, and I would just write Ka for, you can just think about this as the union of this. Okay, so, and just for simplicity, and what we'd like to address is there a natural reduction in walk crossing morphisms for these moduli spaces when the weight changes? Okay, so first of all, what should be the expected picture? So for instance, for the reduction morphism, the expectation is quite easy to come up. So just like in the case of curve, the most obvious thing to do is, so if I take a stable pair whose coefficients are my chosen A, and I want to drop the weights, maybe d prime. Okay, so if I just drop the weights, then usually the singularity condition is okay, but we lose ampleness. So what you have to do from there, just like in the case of curve, is to contract those components where that positivity is no longer there. So for us in birational geometry, again, this means taking the ample model of this log canonical divisor, and hopefully you end up with a new pair. Maybe I don't use d prime here, and let me call it. So I got a new pair x prime d prime, and hopefully that would be my replacement. And if I can do this in family, I would get a well-defined reduction morphism between these moduli spaces. And again, you have to impose certain conditions on the weights pi. So for instance, if I want to drop the weights, I'd better ensure that this log canonical divisor is still big. So there is some admissible condition that will come up shortly. Okay, so, but at least that's the expected picture. Now, now there are some issues here in higher dimension, which you don't see in the case of curve. So the first one is that, so if you want to take this ample model construction, you can usually decompose it in 2 steps. So first you run an MMP, and then once you have the MMP, you show that this log canonical divisor is actually semi-ample, so you can take the ample model. However, although MMP is usually expected to work for log canonical pairs, the stable pairs over there, they are only semi-log canonical. So there are some issues here. So if I have x comma d, which is a semi-log canonical pair that's not normal, and you can even assume that kx plus d is big, then in this case, it's known that so the first issue is that there exists such pair where the section ring of this log canonical divisor is not finally generated. And so, for instance, there are examples by Collar where you can even take the boundary to be 0. And in terms of the MMP, the issue is again that, so if I want to run the MMP on the semi-log canonical pair, so I can first run it on the normalization. However, if I have a semi-log canonical pair that's glued together by several different pieces, then this MMP on the different components, so if I run the MMP on different components, and I get something else, but then these 2 separate MMP might have different behavior on the locus that are glued together originally. So after this MMP step, they might not be able to glue them together anymore. So that's one of the issues. There's a second issue that's really related, but we will get to that later. Okay, so this, what this is saying is that also MMP, the minimal model program, also fails in general for semi-log canonical, and for semi-log canonical pairs that are not normal. So I don't have an explicit example, at least not on top of my head, where the MMP works fails for irreducible but not normal pair. But again, I would expect that something like that would happen as well. Okay, so right, so that's the first thing that we have to deal with. Yeah, so I guess I forgot a condition. You have to impose some condition on the behavior of this MMP when you restrict to the double locus, basically. Then you can glue the flips whatsoever together at the end. Yeah. It's always about how this MMP is restricted to the double locus and the gluing. Okay, so that's the first issue. So you can think about this as related to the non-normality of the fibers. And there is a similar issue if the base is not normal. So of course, in the case of curve, all those moduli spaces, they are smooth. But in higher dimensions, the moduli space of stable pairs, they can be highly singular. So in particular, they can be non-normal. So what will happen is that, so if you try to do the ample model in family, this may fail if the base is not normal. And the reason is very much similar to this. You just have to flip the picture. So let's say if you have a family over this union up to P1, and you have two different families. Now maybe on this family, when you run the MMP, you would end up with a divisorial contraction along all the fibers. But if you run the same MMP on the other family, you may end up with a flip in the central fiber. So in other words, so what you see as the divisorial contraction over here will become a flipping contraction on the other components. So you have to flip it again. So in that case, if you try to glue the two new families together, they don't match along the central fiber. Okay, so you can have divisorial contraction and a flip along different components when you change the weights, say. Okay, so this means that so after the MMP, this family doesn't glue together. The new family don't glue. Okay, so that's another issue. So this suggests that maybe in higher dimension, the best thing we can do is not, at least for in terms of this reduction morphism, it's not defined on the original moduli space, but rather some kind of modification. Okay, so at least, for instance, so we start with that moduli space with this weight vector. So first of all, we'll have to throw away the components whose generic points are not normal, okay? Because we are not able to run any kind of ample model construction for those pairs in general. So first of all, we are going to restrict to the components where the generic point is ample. Okay, or basically that means they are log canonical. So components, so this the union of components whose generic point parameterized normal, which is the same as log canonical in this case, normal stable pairs. And hopefully this is not too bad, because if you have a semi-log canonical pair that's not normal, then basically they are glued together by taking two normal ones. So in terms of the moduli space, we don't lose that much. Okay, so that's the first modification we have to do. And now again, this might have several components and it might not be normal. So we have to fix the second issue as well. And the easiest way to do this is by taking the normalization. Okay, so let me put the declaration new here. So this is the normalization. Let me write it on the left. Okay, so this is the normalization of the components where the generic points parameterize normal objects. Okay, so with this setup, I can at least state one of the main theorems informally. And as I said earlier, this joined with Fan Junmeng. That so informally, basically contains most of the essential information, namely that so for any admissible weights, A and B, where A is at least bigger than the other. Again, so they sit in this region for the correct number of entries. There exists this reduction morphisms. Between those spaces when you vary the weights. Okay, so at least that's an informal statement. And why is this informal? Because, well, so there are many components here that could be infinitely many if you choose different volume. So the meaning of admissible would depend on which component that you are looking. Okay, so if you want to state it more precisely, maybe it's better, so more precisely. So what we're actually proving is that, so if I just take one of the components and look at the universal family, so let's say I have B is one of the components. Okay, so this is normal. And so I have a universal family or a stable family. Where X is where the total space X is normal. Then the real claim here the claim is that, so if you choose any admissible weights, so if you choose a weight that's between 0 and AI, such that if I drop the weights to B, this is still big over the base. I can take an ample model construction in family. So then this kx over B plus the sum of the bi di. So then the ample model of this exists. And that would give me a stable family, so a family of stable pairs over the same base. Okay, so then this would induce over B. So in particular, I get a map from B to the corresponding moduli space with coefficient B. And of course, it will factor through that. Okay, so that's the more precise content of the theorem. Okay, so that's the reduction part. And what about walk crossing? So again, for walk crossing, because there are so many components over there, possibly infinitely many, so it's better to talk about walk crossing after fixing one family. Okay, so, but again, that's basically a finiteness of model statement. Okay, so So that's this part is relatively easier. Okay, so for the walk crossing, what we can say is that so if you fix P to be a polytope, let me just say an admissible polytope. So a polytope consists of admissible weights in this sense. Then there exists a finite, again, rational, well, if you have a rational polytope, then rational. Let me just say finite polyhedral decomposition. Decomposition. With the same picture for curve holes, such that, let me just write it in a more convenient language, such that this reduction map, so fix your family. So I fix this stable family. So I would just write such that this reduction morphism is independent of B as long as you vary the coefficients in the same chamber, okay, interior of the same chamber. And okay, so I'm a little bit short of space here. So I'll continue it on this one. So in higher dimension, it's not necessarily true that the image is the entire moduli space. So there's walk crossing morphisms. So if I call Mi to be the image of this map, where again, so this B lies in the open chamber. Then there exists this walk crossing morphisms. Between Mi to Mj, and so if J is a face, then you get these walk crossing morphisms, and of course they commute with this reduction, right? Okay, so that's the entire statement. All right, so okay, so at least that's the main statement. So now let me try to explain what's the what are some of the content of the proof. So yeah. So you mean in the SLC setting, right? So in the general setting, so I don't have a explicit family where with a generic fiber, like the generic point parameterized an SLC pair, and then once you run the once you drop the coefficient, this ample model doesn't exist. But there are definitely semi-log canonical pairs where the ample model doesn't exist. So I would expect that the semi-log canonical case is a little bit too much to hope for.
Somehow, the SLC pair, you can regard it as LC pair with some like involution of the divisor. You can imagine each component you have a two morphism up to the restriction of the Kernow divisor and the fiber product. So if there's two morphisms both have like reduction map, which coincides on the conductor, that might give the
Right. So at least you would need some extra conditions, yeah, if you along the double locus. Yeah. It's not automatic. That's what I'm saying. Right. So okay. So let me see. Yeah. And by the way, so I should remark that before I go over the proof. So if you replace the where's the notation? Right. So if you don't consider components whose direct fibers are log canonical, but instead you consider the locus that are the normalization of the normalized closure of the points that parameterize KLT as stable pairs. Then there exists. Then the reduction and walk crossing morphisms for this object are studied already earlier by Kenny Asher, Bellari, in Kyosho and Patakabi. So what they show is that basically the same type of statement, but with KLT instead of log canonical. And walk crossing, etc. Okay, so yes, 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 yes. It's a morphism between the stack. So basically, it's what we are doing over here. So once you take the ample model, the space doesn't change. So just by the moduli function, you get a map from the other moduli space. Yeah, it's like the closure of the locus, because the KLT is like an open locus. Yeah, so it's the closure of the locus that parameterize KLT stable pairs, and they will normalize it. So it's usually like a sub-variety or substack rather than the components. Okay, so now I can try to explain what's actually going on behind this statement. And I think I'll mainly focus on the reduction part, because the walk crossing part, as I said, is basically a finiteness of model statement. So so what happens for this reduction part? Well, so maybe we can think about the easiest case where, let's say, so for this precise version, so there is first of all a pointwise statement where the base is just a point. Okay, so then in that case, what we really want to show is that if I have a stable pair like that, which is log canonical, then whenever you drop the coefficient, and assuming that the log canonical divisor is big, then I can run the MMP and get a good minimum model. So that's basically the statement. So in fact, we prove a slightly more general statement. Which says that so if you have x comma d, let me just write. Okay, so these then the sum of this AIDI, and let's assume that this. So I have a pair that already has good minimum model. In particular, this would be true if the pair is stable, because kx plus d is ample. So in particular, xd is stable because we already have this is ample. Then the conclusion is that for any coefficient between ai and 0, but not 0, the new pair that we obtain by dropping the coefficient from A to B also has a good minimum model, or otherwise it would have a Mori fiber space. So I would just say has a good minimum model or a Mori fiber space. So in particular, this allows us to take the ample model if you assume this pair is big. So in the setting of the reduction morphism, yes. So in that case, you will automatically get the ample model. But in general, of course, it can be not big, but you still have a good minimum model in that case. Okay, so why is this plausible? And by the way, so here, one small issue which is not so important is that once you drop the coefficient, then it might happen that this kx plus the boundary is not necessarily Q Cartier, or you can always do a DLT modification to fix that, to make it Q Cartier. But for simplicity, you can just assume everything is like the variety is Q factorial, for instance. Maybe I have to say this again, log canonical. So everything has to be normal. All right, so why is this plausible? Well, so let me remind you some of the theorems that was already known before. So for instance, one special case of this was already proven by Kocher, where he actually proved a much stronger result, and I guess it's also independently proven by Heiken and Xu. That so, for instance, if kx plus d, okay, so maybe I didn't write the statement over. So you can actually do this over base. Okay, so what they prove here is that if this pair is actually not just have a good minimum model, but it's actually log Calabi-Yau, then any boundary divisor that's smaller than or equal to the given one will have a good minimum model. Or Mori fiber space. I just write GMM or Mori fiber space over the same base. All right, so that's like the Kodara dimension 0 case. And of course, there is also a Kodara dimension, the maximal Kodara dimension case where you assume kx plus d is ample, and this d prime is smaller than or equal to d, but not 0. And maybe you have to assume that in this case, this is Q Cartier, let's say. And then why does this have a good minimum model or Murray fiber space? Well, in this case, you can always write d prime as a convex combination of some d0 and the original d, okay? Because I assume that the coefficients are not 0, so you can always draw a line between d and d prime and continue. So because of this, this kx plus d prime is basically proportional to kx plus d0. So it's a convex combination of kx plus d0 and kx plus d, but the other part is ample, so it's basically proportional to so a log canonical pair plus something ample. Okay, so because of this, we already know MMP with scaling would work for a log canonical pair. So again, this would tells you the existence of good minimal model or Mori fiber space. Okay, so these are basically two extremes, and in the middle you have to interpolate them, but that's roughly how it works. Right, so that's that will give you a pointwise statement for this reduction map. If you just have one fiber. Now, if you want to do this in general, we have to run the ample model construction in family. So here the issue is that, so of course in general we can also run MMP over family, but the problem with this stable family is that the basic can be very bad. So in particular, if you look at the total space here, it's not necessarily log canonical, even though the fibers are. So the second statement we have to prove here is that you can also run the MMP in this setting. So for any, so this is called a locally stable family. XD over B, where X and B are both normal. Okay, and the locally stable condition basically means that the fibers are semi-loc-canonical. Okay, so we are not assuming the emptiness condition anymore. Okay. So what you want is that this Kx plus B plus D, this is it's a Q card here, and the fibers of this family, okay, so earlier are semi-loc-canonical. Okay. The total space, so the generic fibers are loc-canonical, but the special ones might be semi-loc-canonical. Okay, so that's the meaning. So the conclusion is that so then we can then for any ample divisor, relatively ample divisor on this family, I can run the MMP for this divisor with the scaling. And of course, and just as usual, it terminates with a good minimum model if the generic fiber has a good minimum model. Okay, and of course, generically, this is loc-canonical. So I can use the ones that's already there. Okay, so now earlier I mentioned that this locally stable families, the total space is not loc-canonical, but at least what's easy to show is that if you do a base change, or if you do a log resolution of the base and pull back the family over the log resolution, then what you get would be loc-canonical. So at least you can run the relative minimum model program over the resolution. So what is really going on here is that that family descends. Those MMP steps descends. Let me mark it over here. So basically what this is a descent statement. So you start with the original locally stable family. You can do a log resolution and pull back. Then here, this is loc-canonical. So I can run the MMP and try to descend everything. So there are two different kinds of statement. So there are extremal contractions. And this descend by some kind of invariance of Fourier general. For families of good minimum models. Okay. And there are also flips. And the reason this descend is because, and this is where we need the base to be normal. Okay, so actually this descend even to any reduced space. but the flips really only descend along the normal base just by the reason that I gave you earlier for the second issue. So this descend along normal base range. And basically the reason is that if you try to do a flip here, so if you consider a point over B and look at the fibers, then they are basically like flips of the same stable pair. But in some sense, there are only finitely many models that you can obtain by taking this flip. But if this is normal, then the exceptional locus is connected. So if you want to put finitely many models varying with a variation over the connected base, then there is no variation at all. So they descend. Okay, so this is because of some finiteness of model. Okay, and then after you have these two steps, then we can construct the reduction morphism. Okay, so maybe in the last 5 minutes, let me just add one quick remark. So so earlier when I talk about these reduction morphisms, I always keep the coefficient positive. But in fact, even in the case of curve, there is also a so-called forgettable morphism where you just drop one of the coefficient to 0. So you remove one mark point, basically. So here we are unable to do that. So the question is, so what if I drop the coefficient just to 0? So I'm forgetting one Mach divisor. The reason is that so we expect this to work even in higher dimension, but this would be essentially equivalent to the abundance conjecture. So the reason is that so if I take an arbitrary pair that is already a minimum model, and I choose some ample divisor, then of course if I perturb it a little bit, then this would be a stable pair with some generic choice of a boundary divisor. Now if I want to drop the coefficient to 0, I need to solve the abundance for this kind of pair. So we don't know how to do that yet. And if someone has a good idea, please let us know. Right, so this will require abundance. And basically you can see why it works for the KLT case. So in the KLT case, the abundance is much easier for those KLT pairs of log zero type. So basically what we are trying to do here is to work out the existence of polynomial model in the best possible region. Yeah, sure. So whenever abundance holds, then we have the answer. Okay, I'll stop here.